Cool. Well, hi everyone. Obviously, yes, I'm Josh. So my presentation today is based off a project that we did for Auckland Light Rail, but it's kind of a process that we've evolved out from things like Sydney Light Rail, and we've also used a similar technology on Parramatta Light Rail. And we're in the process at the moment of expanding this out to other linear projects like Year Road in particular. So it's got a pretty straightforward brief. So we had a team of utility engineers manually going through. They'd converted a whole heap of network utility owner data from GIS to CAD for some unknown reason, and they were actually going through in CAD and trimming everything down, taking the coordinates back out, and then placing that in a spreadsheet. You're then using that spreadsheet as their basis for analysis of what treatments they were going to do. So the first step was pretty much automate that and kind of stop that straight away. They had constant alignment tweaking, which was kind of a bane of every design engineering project. Might only be a half metre here, half metre there, or might be a little pinch vertically, but it was quite annoying to deal with. And probably the key one out of this process is the standardisation to AS5488. So that's a ABCD classification for the confidence you have in the location of the underground utility. We've utilised it for a lot of projects now. We've kind of bastardised it for other projects for location of like other survey features and things like that. Had a plethora of network utility owner data come in a variety of formats. I think we had about 8 different formats it was coming from, and they decided to all have their own individual schemas naturally, because that's the best way to work. And we had around about 100,000 assets that we had to push through this process. As part of this as well, we actually developed a schema on the output side. So we wanted to standardise all the attributes that we were getting from the network utility owners and have it in a way that we could give it to the engineers and they would look at it and go, well, that's an invert, that's an obvert, that's a depth, rather than kind of looking at it and going, oh, that's OB, or that's IL, what is that? Which was quite important to kind of help them speed up their process. Another little sexy tram. So one of the network utility owners decided that to store all their comms data, the best format for that was CAD. I'll just leave that there, I think. We got you can see in the top right corner there, we got the drawing files back from them, which is very, very detailed. It's awesome if you're going to sit and manually go through everything, which is an absolute nightmare if you want to try and automate. So what we've got there in the top right, in the top left corner of the top right image, I made that easy. You can see it's got a little section marker. So each of the blue lines is a center line of a duct bank. So then you get a little section marker which actually relates to that block blowout there. And each one of those block blowouts as well has a name. So in particular, this one's 9A. So what we did is we set up a process that would actually associate, so it's just spatial overlaying that section block on top of the center lines, and then we would actually associate all the information from that attribute block back to that center line, which you can kind of see through the bottom left there. What we actually did on top of that is we had to actually extract out what number it was. So we had, P1 would be 110 mil, and we actually had the contents of that, which is TSL, which is a service provider. And then we would associate that back. So we actually cloned each of the center lines by however many times there was a duct, which brings me on to my next slide, which is it's interactive. So we had the center line string, and then we actually would clone that by the amount of times from the attribute name. So then we would actually offset. So the offsetting we did between each of the ducts was actually the maximum duct size for the bank. So in this case, there's one right down the bottom, which is a 50 mil, and all the rest are 110. So our offset spacings would be 110 mils. I don't know what that is in imperial, sorry. And then we'd offset one side, offset the other side, and then work our way down. So these are just vertical offsets and a few expression evaluators. But we had a lot of custom duct configurations. Like you can see, this guy here is actually a 9 configuration. So we also had that guy, which kind of hit away. It was a bit of a manual process in setting up a spreadsheet to actually map all these out in their locations. because they varied quite significantly. On top of that, we also had the network utility data, and we also had a topographic survey that come back through. A lot of the network utility data might be, well, we've got a pit somewhere in this 5 metre radius, happy days, if you hit it, it's your fault kind of thing. So we went through and had a process of that. They'd gone through and done a topo survey, and we could actually take out the drainage survey pit extents and then overlay that on the network utility owner points. So we could actually take out the geometry, the survey geometry, so we effectively turned it into a survey accurate pit. And for any ones that we didn't actually have survey geometry for, we had like an assumed size. We usually over-egg those as well, so we wanted to make them bigger than what they actually were, because it's always better to have more clashes than not enough, and you dig them up with the backhoe. And then, so if any of the points fitted in, it was top row, and if it was just outside, it would fail and go on the bottom. We ended up having probably around about maybe 80% were classified through this process, which was kind of good. Unfortunately, we did have like the top right there where it's got the triangle polygon. That was kind of, we just owned it with what it was. Unfortunately, there's some triangles got through. In addition to this sort of 2D rectification, we also did some 3D side of things. So we had DEM of the whole project. So on top of that, we had the 2D GIS. So what we'd actually do is drape the strings on top. We'd only use the vertex rather than the full model. So we'd actually get the start and end nodes would be on top of the terrain. And then we actually had an assumed depth. So very similar to the assumed size, we had because the nature of light rail, we got like a nice track slab. So we kind of raised up all our assumed depths so that we would get a hit if it had an assumed depth. And anything that had absolutely any values assumed on it would be classification D, with classification A being that you've touched the pipe, it's there, you know how old it is. So the analysis side, another cool tram pick. So we did a 2.5D clip. This was actually more of a mathematical clip. So we just did a 2D kind of cookie cutter clip. So you'd end up with a result like that. And then what we would do is we knew the bounding box for the track slab. So you'd end up with you could just check the elevation. So if the start or the end elevation was within that track slab, there would be I've got the colours the wrong way around, I suppose. So green would be a pass, so that would actually be a clash, and red would be a fail. So that would be a hard classification. So you'd use the inverts and the obvert levels. So we actually calculated if there wasn't an existing obvert, we would actually use the pipe size to offset that value back up. But we also had, so for AS5488, there is a tolerance, like a horizontal and a vertical tolerance. So say if this was classification D, we would then add another 1.5 metres onto that to kind of pull it up to make sure that we had a clash to kind of cover ourselves. So another kind of cool thing that we did, we took into account the interaction with design. So we had the centre lines from design, and then also took the angle of the actual asset itself. We would calculate those back against each other to determine whether it was a perpendicular or a parallel clash with the alignment, or if it was a node clash as well. So the node clash was actually a bit easier because we just went, it's a point, it's in 2D, so if it's a manhole or something, it's got to come to the surface, we're going to hit it. But it was quite, we used it for the kind of the next couple steps, which I'll get to in a second. Oh, next slide, sorry. So that was really loud. So post that initial kind of cookie cutter and the 2.5D clip stage, we've got the interaction with design. We went through with the network utility owners and set up kind of a logic tree of how they wanted to classify their features. So you got your red, amber, green values for your risk of how dangerous it is to be interacting with those. For this instance, we've got gas, which you can see up the top there. It's a high pressure gas main. It's a red risk straight away. We don't want to get anywhere near those. And then we took into account like whether it was a polyethylene, it was less than 50 mils, and the K road. So there was it was a cut and cover structure for the project, and we also had another zone in addition to our track slab zone, which we call the kinetic envelope. So when you got your tram, you can't have anyone within a certain zone. And if we had a manhole that ended within that zone, that would automatically be a failure as well. But we also had, as part of this logic as well, if the start or the end node was within the kinetic envelope, that would actually be a divert automatically for the asset that went between the two nodes. And yeah, the fragility of the materials as well, which is pretty important. So that guy is down the bottom, so that previous slide. We could have probably bundled these transformers a bit better, had it as one big test filter, or one test filter for each network utility owner. But sitting there with the network engineers, they kind of wanted to see where things were getting filtered off and getting broken away, rather than having just oh yeah, you've got 50 red and 100 green, which is quite painful. On top of that, the risk logic, we also set up a high-level treatment logic. And this would actually go through whether it was to be a divert, leave, protect, or if it required manual assessment. So manual assessment tended to be for features that didn't quite easily fit within one of the previous categories. And this was just set up through functional logic. So it was like, if it is made out of steel and it is a high pressure main, then that would have to be diverted. But that would also take into account things like how it interacted with the alignment. And then we also took into account things like cover as well. So if it might be acceptable, might be underneath the design enough, or the track slab enough, but the actual cover between the two, we couldn't fit in a protection slab or anything like that, so it would actually be a divert from there. Other cool things on that as well was we had if the protection length was over 20 metres, we would actually revert that back to being a manual, because protection slabs over 20 metres kind of get pretty costly as well. So the kind of cool part, I suppose, or the kind of Easter egg, I suppose, of this, is we had, out of the whole process, we had about 5,500 clashes come out of this model, but probably around about 4,800 of those were classified through the functional logic, and then we thought, what else can we do with these extra ones? You still got quite a few manual detections to go through. So we pushed all the training data up into an Azure table on Azure. And then we actually had a neural network as well. So we actually trained the neural network, which is just effectively a HTTP caller, so nothing too fancy there. And then once that neural network had actually been trained, because of the amount of time it would take to train that, we actually put a feature holder in, just to kind of stop everything from trying to punch through before the actual neural network was trained. That's what the tester's kind of doing, is just taking out that single response back from the HTTP caller. And then all the other features that had failed had gone through a request body generator, which is just string concatenator. I thought I'd name it a bit fancier. And then on that, it would actually go through another HTTP caller and request a score. So the results from that, we had around about 60% passed, or actually got a good value, and that was based on 70% probability. So if we had anything over 70% probability, it would retain its value, but anything less than 70% probability of a score would then be dropped off and go back to being a manual. And that was kind of our initial idea to set up this. Was I gave the network utility engineers like 20 features and said, you guys go and manually process those, whether it's going to be a divert, a leave, or replace. And then I went and pushed them through a whole series of different machine learning algorithms. So you had things like neural networks, decision forests, and decision jungles. And then I kind of tweaked on the parameters in those as well, just to try and get the best possible probabilities back out of that. And the outputs of our project, another cool tram. I don't know if anyone's noticed, I've been mixing them up from around the world. So we had a WebGIS that the results were automatically getting output to. So there's a geodatabase sitting behind there with dynamic tile cache. So from when I would get the inputs, maybe a new alignment, process that whole way through, within 15 minutes, the guys could be jumping on the WebGIS and actually interrogating those results. Sometimes even before I'd sent them their other outputs as well. One thing we did add as well is a GeoID. So every single pipe string, every single pit would have a GeoID associated to them, and then that would actually be used for our data lineage the whole way back through. So you could actually effectively jump on the WebGIS, search one GeoID, and you would actually see all the iterations of the clash detection process plus the original feature. The other kind of output, which is a bit old school, but still useful. We output spreadsheets for them. So we had a lot of conditional formatting that they wanted to put in. So for the red, amber, green, and also the high-level treatment codes, they wanted to have some conditional formatting on that. But one really kind of cool thing that we did for them as well is we had a hyperlink to the survey documents, which I'll cover off how we generated those in a little bit. But if you want to ever output a formula to Excel, just do the attribute name and then .formula at the end, and just type the formula as you would in Excel, which is really, really quite useful. At first I thought I was a bit skeptical, but it was useful to output the links for the guys. And other useful stuff that we did. So we built, setting light rail was quite a manual process. We had the workbench for that, I think it was about 3,000 transformers, or thereabouts. And it was quite a cumbersome beast. If someone wanted to do an update, it'd take you 3 or 4 hours to find out where exactly it was, update that, run the process to make sure it was all okay. So we set up a series of custom transformers and tried to make all the inputs for that dynamic across the project. A lot of attribute value mapping as well. And actually in some of those as well, there's a lot of regex to kind of do some string searching and stuff like that. Next slide, this is actually our overall workbench. I don't know whether many of you are kind of familiar with how big a workbench file can actually get. This one's 17 meg all up, which I think the normal ones are maybe kind of 3 or 4 meg. And it had around about 1,500 transformers in it. So that's actually one of the kind of lesser complex network utility owners. And within there was a lot of regex. I don't know whose idea it was, but the network utility owners decided to compress everything up and concatenate stuff into one field, which is probably great, makes things really legible for them, but it's an absolute nightmare to reverse engineer and scrape that back out. And some of the information as well was within different databases that would send through. So like if it had asbestos or lead contamination, that was in a completely separate database that we would have to join those up. And where possible, we tried to actually convert things to FFS and then pull them back in because it was a bit quicker than trying to read in a full DEM. And so the sheet layout hyperlinking I mentioned just before. I know I've stuffed up the points on this one, so my animation is not going to look right. So what we had is the CAD team, when they set up their design, they've got a whole heap of sheet layouts that usually follow the alignment. It's that alignment matches what their output drawings are. So we had a whole series of polygons, and pretend that green dot is a piece of text, but they are all overlaid with a text value. So we actually overlaid the two, so that would be sheet 1, sheet 2, sheet 3 for the whole alignment. So we'd associate those two back, which is completely out of order. Sorry about that. So we'd had the end output of it would be actually a polygon which would have that sheet number associated to it. So you would have the value of 1, 2, or 3. And then from there, still one more. We actually could do generate some hyperlinks out from that. This one in particular was just pointing directly to our WebGIS server, but you could point it to things like ProjectWise, web interface as well. And the formula down the bottom there is not hugely complex. It's just effectively join this with this, add the sheet number and PDF on the end. But they really, really appreciated it because it was on all of the outputs. And then sometimes if you'd had an older version, we'd actually associate it back to that version. So like for our detailed design, there'd be another PDF called DD, and it'd be linked back. So you could actually have that kind of lineage not only on the GIS side, but actually on the PDF side. Another step that we also added was some automated superseding, mostly because the data lineage is quite important. So what we'd actually have is, before we'd actually output our geodatabase, it would take a copy of that and put it into a dated folder. And then before it went to process the next step out. Probably the next thing I've started tinkering with after this is actually having automated feature dataset creation. But because we were doing a dynamic tile cache, the actual feature class name was the same for our outputs each time. So taking that copy of the old database was quite important. And because we have that same feature class name each time, we don't have to actually update anything. It just drops table, pushes the new one in the background, and no one's the wiser. So conclusions from this process so far. I think probably the biggest one that we've had a lot of lot of appreciation for, is that the process previously was around about 860 hours to go through and process. You do your clip, and I'd go home for the day, and the utilities would sit there fumbling along for quite a few days, weeks, sometimes months. But our process actually automated that down. So if you take out the 100 hours it was for me to set up that analysis process, you're still saving about 700 hours just on the clash detection analysis side of it. That was probably the biggest thing, and we've actually won an award off this as well. So the Asset Management Council of Australia just gave us an award, I think maybe 2.5 months ago, for information management based off of our analysis. And that 700 hours saving isn't just for that one run. That's it. It's actually for each run. The guys have to go back through and manually do a clash detection analysis. And other things that were really good is it wasn't someone sitting there trying to transcribe from DWG to a PDF to a spreadsheet to a SQL database or anything like that. It was just one process. Here's your outputs. You guys go away and make it happen. And yeah, so that's probably me. I know I probably finished way early.
No, you're
okay.
You're great. Thank you very much, Josh. Are there any questions for Josh? So you were saying, maybe I have a question for you. Which you were sort of mentioning at the end about how long, I guess in terms of it used to take, like it was much more time consuming, and now going to the 100 hours, it has a much better efficacy in terms of getting your output. So I don't know if you've done any quantifications of after how it's going now.
It's down to 3 hours now from start to finish, and that's if we get new network utility owner data as well. So it's quite a significant saving, and I suppose the guys are quite confident in it as well now, because we did give them those 20 kind of test features and then ran it on through the neural network as well. Because the first part that would take him way too much time for an engineer to sit there and go, oh no, it's a divert, or it's a leave, or it's a red. So even just the functional logic side of things saved a lot of time.
So there's good uptake.
Yeah, it was excellent uptake. Yeah, and we're actually trying to roll this out on other projects globally as well now. So there's a couple in Europe as well I'm aware of.
Cool.
Sweet.
The neural net that you were calling through HTTP, was that something that you implemented yourself?
That's correct, yeah. So we've got like an internal, it's like kind of a collaborative role. Help me out here. So we do like an internal course where we collaborate with a university. So I did the big data module, and I collaborated with University College London, where we learned about neural networks and big data analytics and stuff like that. And that was actually because I kind of was working too much on Auckland Light Rail. I almost ran out of time to do my assignment. So I was like, well, let's just throw this in there. So I kind of bundled work with study, and that was why we decided to use a neural network and kind of went through that whole assessment process as well, rather than just going, I'm just going to the neural network because it sounds cool. It was actually a full analysis piece behind that as well.
Well, thank you very much, Josh.
Thank you.